Hi, everybody, and welcome to the webinar on designing for IoT networks in warehouse environments. My name is Kelly, and I'm going to be your moderator for today. Before we jump into the webinar itself, there's just a couple of housekeeping rules I wanted to go over. The first is that the webinar is being recorded, and we will send a copy to you after the webinar, so you can expect that in your inbox probably tomorrow. And the second is questions. If you have any questions throughout the webinar, please use the GoToWebinar box to ask them, and then we're going to get to as many questions as we can at the end of the webinar, and possibly we'll try to fit in a few as we go throughout the webinar. And with that, we can get started. To do that, I'd like to introduce our speaker, Dr. Vladan Jevremovic, our Senior Research Director here at iBwave. Vladan, over to you.
Thank you, Kelly. Hello, everybody. Let's get started with the presentation. On our agenda today is the following. I will be talking about IoT standards. I will give you overview, and I will focus on the most popular ones. Then we will talk about specifics for designing Wi-Fi IoT network in a warehouse, and also with specific of designing a Wi-Fi network in industrial manufacturing. And then after that, we will spend about 15 to 20 minutes on a demo that will show effective IoT design, Wi-Fi IoT design in a warehouse. So first, let's talk about all IoT standards that we have. I have given you here a list. There are quite a few of them that have adoption rate that ranges from very low to moderate to high and very high. And there are a few of them that are upcoming technologies. The very, very popular technology for IoT is Wi-Fi or 802.11. It is, in my estimate, it is probably about 80% of IoT networks that we have today indoor are Wi-Fi networks. And the popularity comes from the point in time where 802.11b and G have been developed, and that was the first wave of IoT sensors and devices, and quite a few of them are still operational. We will touch on that subject later on. And then there are some moderate technologies like LoRa and Sigfox, and they are proprietary technologies, and they have had some success, mostly in outdoor networks. And then there are others like Bluetooth and Zigbee that have created their own niche. We will address both of them later on. They're, how would I say, they are really specific for a particular type of IoT devices. And then there is a 3GPP. 3GPP has quite a few IoT standards, such as NB-LTE, NB-IoT, LTE-M. And we have seen recently some adoption, mostly overseas in Europe, but there are some in North America as well. And then there is 5G. It is not listed here, but I will touch upon 5G IoT use cases, because 5G was developed, or that 3GPP release 15 standard was developed, among others, with IoT in mind. And that standard is supposed to be very IoT friendly, and the 5G or 3GPP standard is, I should say, basically is trying to make inroads and help with the huge adoption of IoT sensors in upcoming years. So the first technology I would like to address is LoRa technology. As I mentioned earlier, this is a proprietary technology, and it is developed by Semtech in France. It operates in sub-1 GHz bands, and it can support long-range links up to 10 kilometers in rural areas. It has a low power consumption, which is really good, meaning that the battery life is going to be in the order of several years. It is used primarily in rural, remote, and offshore industries. And the LoRaWAN is the network on which LoRa operates. It is like Wi-Fi, but for remote and unconnected industries. So at this point, I need to point out why LoRa became so popular for those remote industries and unconnected industries. Namely, the data rate for LoRa devices is very low, on the order of a kilobit per second, and it uses very narrow channels, RF channels. What it really means is that the noise floor is very, very low, which means the sensitivity is very low, at the order of, I think, minus 130 dBm or even lower. So what it means is that the path loss it can sustain is very high. And if you are in a remote area, when there are not that many obstacles, that signal can propagate very, very far. So that is the reason why this technology has seen some success in those particular industries. If you can go up to 10 kilometers with your link, and providing that your sensors do not really communicate very often with the base, and the battery can last several years, it is easy to see why this technology has seen some success in outdoor applications. Then the next one is Zigbee. It is a 802.11.15.4 technology. It operates at 2.4 gigahertz. And having said that, it operates in the same spectrum as Wi-Fi, and basically is a competitor with Wi-Fi over airtime in that spectrum, and we will mention that later on. Its characteristics are low transmit power, low data rate, but it is significantly higher than LoRa's data rate. This one is at the order of 250 kilobits per second. The signal range is much, much lower. It is from 10 to about 100 meters, depending on the environment, low battery consumption, and secure transmission, which is very important. This is a cheaper alternative to Bluetooth and Wi-Fi, and it is used for home energy monitoring, for wireless light switches, and for traffic management. As we already mentioned Bluetooth, now we are going to expand a bit on it. This is a proprietary technology which was developed by Ericsson. It operates in master-slave configuration, and there are 3 different classes of Bluetooth radios. It can be between 0 and 20 dBm power, those 3 classes. The range, depending on the transmit power, can be as short as 1 meter and as long as 30 meters. And it can send up to 2 megabits per second, which is significantly higher than the previous 2 standards mentioned. But the use cases are very specific. As most of us know, mobile phone to handset connection is a Bluetooth connection. The connection from your mobile to your car is also Bluetooth. The connection to your mobile to wireless speaker is also Bluetooth. So those are all Bluetooth, but the new one is wearables. Now, if you have a smartwatch, connection from your phone to your smartwatch is also Bluetooth. And also real-time location systems are what operates on Bluetooth. And then we finally get to Wi-Fi. This is a IEEE 802.11 standard. It has a very high adoption. Most indoor IoT operate on Wi-Fi. And there are a lot of old IoT sensors, 802.11bg, which are still operational. So what is next for Wi-Fi? There has been a standard that has been closed, that has been developed, and it is 802.11ah. It is also called Halo, and it operates at 900 megahertz, which is different than what other 802.11 standards operate at. The reason why it goes to low to 900 megahertz is because the propagation characteristics are more favorable, and thus the range can go up to 1 kilometer. So the idea is for this standard to be a standard that is used for IoT applications outdoors. On the other hand, 8.11ax has been developed with a lot of IoT-friendly features in mind. This is targeted wake time, which allows the battery consumption to be lower and for battery to last longer, and up to 18 clients can send data at the same time, because we now can partition RF channel in smaller chunks, which allows more users to be served simultaneously. And there is also OFDMA technology, and that last A means access. It means that multiple UEs, multiple IoT sensors can connect at the same time to a different smaller chunks of frequency. Now there is 5G, and 5G brings efficiency to cellular-based IoT network. And cellular-based IoT network is what we have with those 4G IoT standards that I mentioned earlier, namely NB-IoT and LTE-M and so on and so forth. 5G can provide very low latency and connect million IoT devices per square kilometer. This was one of the main requirements for 5G technology. This can help address outdoor IoT in ways other technologies cannot, which is low latency and high sensor density. And it has lots of IoT-friendly features, but it will really be difficult to unseat Wi-Fi as undisputed indoor IoT network provider. So my opinion is that 5G standard probably will successfully enter the outdoor IoT arena, but as for indoor IoT, there is a long road ahead for 5G to unseat Wi-Fi as an undisputed leader in indoor IoT networks. Now I have prepared a few more slides where I will address a couple of IoT use cases, because 5G IoT is such a fascinating topic these days. The first one is smart factory, and enhanced human-to-machine interface will increase in the future, which will bring augmented reality. 3D printers will be used more, and machines will be connected and have artificial intelligence feedback. And the supply chain will be more connected and tightly integrated. Now, for those artificial intelligence and augmented reality, what we really need for that is very, very low latency. And so what I envision, for smart factory is applications that are really critical from the point of low latency, and probably some that are critical for video monitoring with high resolution video. That is something that 5G should be able to do very, very well. So those applications are what I see 5G being successful at. And here I have shown you a smart factory visual, and here is listed value chains from suppliers onto to component manufacturing, press shop, body shop, paint shop, final assembly, and finally the customer, and support systems from digital plant logistics, product simulations, and assistance systems. In each one of them, there is an application where 5G IoT can step right in. For example, smart robots. You really do want to have a very short latency if you have smart robots in your assembly line. Then there is others such as smart presses and predictive maintenance, where IoT should also be benefiting from 5G features. Smart robots again in a body shop. And then we have data-driven quality control and smart robots again in final assembly. So everything where you see robotics, we envision that low latency will be needed, and also machine learning later on will benefit from that as well. So that is how 5G can help smart factory in the future. And then there is oil and mining industry. There, what we will need is high bandwidth sensor applications where you need video. Equipment inspection by autonomous vehicles, again, there is a need for video. Safety and control systems, a need for low latency. And robotics. There as well, you would like to see low latency, and for the robotics would be mining equipment and tractors. But when you have oil and mining picture that I have shown here, then you see that really that industry is deployed over a vast area. And each of those individually will need to have IoT coverage inside, but also there should be an IoT coverage on the outside between those plants. And there, 5G IoT being really good at connecting a large number of sensors over a relatively small area comes into play. For oil and mining, outdoor IoT coverage would be instrumental as well as indoor, and here you see why, because all of those components, all of those plants are spread out, and you would like to have coverage in between them as well as inside them. Having said that, let's move on to warehouse as an example of an indoor IoT venue. And this is a typical warehouse that you see. Some shelves are empty, some shelves are full, but shelves are fairly high, go high almost up to the roof. And essentially what you are seeing here is a kind of a canyon where the signal would propagate in between the shelves. But that canyon can have holes, and that is how it makes it different than, for example, what you have in a, let's say, a hotel, in a hotel where you have an area that leads to the rooms. Yeah, that is obviously a tunnel-like, but it doesn't have holes in it, and it is not made out of metal. So, and it is not, the walls are not 5 feet high. So this is why this environment is very, very specific and deserves being addressed as a separate use case. So what are the design challenges? First one is inventory. The propagation range depends on whether the shelves are full or empty. The tall ceiling, that can be up to 20 meters high. So if you were thinking about putting an omnidirectional antenna on near the ceiling, that may not be a good idea, because indoor omnidirectional antennas, they work best 3 to 5 meters above the ground. Then we have tall shelves. We have shelves that can be anywhere between 3 to 5 to 10 meters tall. And the thing is, those scanners that are going to scan the merchandise need to have coverage along the shelf, top to bottom. So when you are doing a prediction, you have to go and predict what happens a few feet from the ground, then several feet from the ground, and then maybe 10 feet from the ground, and even higher, depending on how high those shelves are. And that is very unique to warehouse. And then there is reflective surface. There is metal ceiling, then metal shelves, and they can cause a lot of reflections. And this can cause excessive bit error rate at the receiver. So those are the network challenges that you would encounter when designing for warehouse. Now, signal survey should be done with full shelves because full shelves are the worst case scenario. You should not do a signal survey when the shelves are empty. And the reason why is we design for worst case to ensure coverage everywhere. If shelves are later emptied, there may be excessive CCI. But, this may slow down the network, but it won't cause signal outage. Now, if you think about that, this is, the scanners really don't send very high, very large data. And then so the data rate there is not really an issue. I'm not saying CCI is not an issue, but I'm saying is that we are not saying a high data rate video, from the scanner back to AP. So high CCI may not be a huge problem if it happens occasionally. So that is the rule number one. Signal survey should be done with full shelves. The second suggestion is to have directional antennas that are parallel to the ground and to be mounted against the wall and to be pointed between the shelves in the direction of the opposite wall. This can be done successfully depending on the configuration of your warehouse and depending on the width of the warehouse. Sometimes you may need to put an antenna that is facing the other one in the opposite direction. Here, I basically put one, facing one on the left and one on the right, and basically avoided antennas pointing at each other to try to minimize CCI. But sometimes you need to do that, and I will show that in an example later on. What goes without saying, those directional antennas should have narrow beams because you do want to focus this energy to flow in between shelves. You do not want this energy to spill over to the next shelf. And then there is in-ground concealed antennas. And I'm mentioning ventive antennas because that's the only manufacturer that I'm aware of that has those in-ground concealed antennas. And here I give you a few pictures that show how those ventive antennas are mounted into the ground and what they look like. This is a very neat trick, and it could be used in warehouse. The only problem is, that there are forklifts milling around. And if your forklift just happens to park itself above a ventive antenna, then you won't have coverage until the forklift moves. And that may be a bad thing. If you have a forklift because you want to go and pick up the equipment and scan it, or just to go up and scan what is 10 feet above the ground, well, you won't have coverage because you just got yourself above that antenna. So that may be an inconvenience, but I figured I would mention these antennas because there may be a good solution for warehouses in some areas. So the next thing, we talked about excessive reflections. So how do we deal with that? We do that by disabling short guard interval. Lots of reflections from metal objects may cause large BER, and large BER may cause excessive retransmission requests, which slows down everybody in the network, not just that one area that may be excessively affected by reflections. Disabling short guard interval may help improve BER and reduce retries. Here I gave you a screenshot of how it can be done at a one particular AP. Enable and disable of short guard intervals is shown here. Now move on to industrial manufacturing. This is how your industrial manufacturing plant typically looks like. What you can see is there is lots of machines, there is lots of robotics, and there is a lot of metal going around. So, in a nutshell, large machinery everywhere, a lot of signal reflection. There is even more reflection than warehouse. And also, unlike warehouse, this may be a very congested 2.4 gigahertz band. Why is that? There are other transmitters, which are non-Wi-Fi transmitters, that work at this band, such as Zigbee or Bluetooth, maybe some others. Then there will be heavy motors. Heavy motors, can emit a signal that is non-RF signal, but it can end up at 2.4 gigahertz and will cause excessive noise. Then there are fluorescent bulbs. Almost every industrial manufacturing plant have those, and their buzz, can go to 900 or 2.4 gigahertz band as well. And then there are video cameras. Video cameras also may use 2.4 gigahertz to transmit the data. So this is a much more congested area than warehouse. So in warehouse, we typically don't have heavy motors. There are far fewer 802.11 transmitters. Obviously, there will be some fluorescent bulbs and might have video cameras. So what do we do with industrial manufacturing? Well, first thing is we have to do spectrum analyzer survey. It is a good idea to do spectrum analyzer survey at warehouses as well, but at industrial manufacturing, it is a must. This is done to determine which machine emits non-RF energy and in which part of the spectrum. And this should be marked on the floor plan to avoid using affected Wi-Fi channels near the machine. And also, we need to know our client capabilities. There may be legacy 802.11g clients, BG clients, that need to be included. And they are slow and they have poor security standard. So must create a separate SSID for those devices to separate them from newer devices, which is 802.11n and AC. And as a matter of fact, what I said here for manufacturing applies to warehouse as well, because there may be scanners that are 802.11b and G scanners, and they should be this option should be enabled at your AP. And your AP obviously should support 802.11b and G. And obviously, a separate SSID should be created for the scanners. Now, having said that, let's move on to the demo. And for the warehouse, design parameters were 3 RF channels at 2.4 and 19 and 5 gigahertz. My target signal was SNEG 73 dBm. Now, why is that? This actually comes as a recommendation for CWNA for low throughput applications, such as these ones, such as scanners. Typically, you would want to look into signal-to-noise ratio, and you would want to have your signal a certain number of dBs higher than your noise. But at a warehouse, we typically don't encounter much noise, so I took a liberty to assume there will not be significant noise, and I said that NEG 73 dBm should be a target signal. Transmit power is NEG 5 dBm at 2.4 gigahertz and 5 dBm at 5 gigahertz. Now, 802.11b and G must be included to support older handheld scanners, but this should be disabled in offices, and there use 802.11n and AC instead. Now, having said that, let's move on to examples. So this is a warehouse, and I'm going to show that in a 3D plan.
Well, Dan, while we're waiting for that, just one question that came up.
Yes.
What are the main design criteria thresholds for IoT in indoor environments?
Well, for IoT in indoor environment, typically you would want to know what your noise level is at the plant, and basically you would want to have your signal to noise ratio at least 18 dB higher than your signal to noise ratio to be 18 dB, which means your signal should be higher by 18 dB than the noise. And if you assume that it turns out that there is not much noise there, then you would be free to assume something like 73 dBm as your signal level, which is what I have done. Now that really is different than when you have a voice application where your signal to noise ratio should be at least 25 dBm. For these applications, when it is low data rate, then 18 dB is enough. And again, if just so happens that you do not really have much noise, then you know, your voice should be neg 67 dBm, and your IoT should be on the order of neg 73 dBm. So here is the view of our factory, of the factory warehouse, and there I want to show you inclined surfaces that basically shows your the view of a roof. So the roof is shown here, and I'm assuming that roof is about 6 meters high. And here is how the shelves are modeled. The shelves are about 3.5 meters high, which is of the order of about 11 feet. And I have various levels of the shelves as well. So in my first example, I'm going to show you what the coverage looks like when the shelves are empty. I also have offices that I need to cover. There is one here in the corner. And there are offices around here. Here the roof is a bit lower and it is horizontal, and I removed the inclined surfaces. But here, obviously, I would want to have some Wi-Fi coverage as well, and here as well. So what we're going to do is we are going to go and take a look at how this looks like when I put in my APs, my directional APs. As I said, I would want to put them, you know, so that they do not face each other. So every other row is addressed. And the question is, how do I choose antennas? Well, if I go to design plan, I'm going to click on this antenna, which is a Wi-Fi MIMO antenna that covers 2.4 gigahertz. Of interest to me is a view pattern, which basically shows me an antenna that has very, very narrow beam width, both horizontal and vertical. It does have some side lobes, but what I really am interested in having an antenna that can properly direct the signal in between those shelves. So narrow beam antenna in both directions is what I'm looking for. I'm also interested in antenna that has similar characteristics at 5 gigahertz because I really want matching patterns. And that's why I have this one, which is from the same manufacturer, but only addresses a different frequency. So it is not identical because it addresses 5 gigahertz, but you can see that it still is narrow beam antenna in both vertical and horizontal. Another thing that I want to point out is, as I said, that B and G should be addressed. This means that I have enabled this AP to support 2.4 B and G technology for that area that is in between shelves. And you see that right here, 2.4, 8.11 BNG. The other ones that are over where the offices are antennas that are omnidirectional and support 8.11n technology. And so the question then is, what is a signal strength in this case? And I ran some simulations. And as you see that for those antennas that are pointing at each other, that are not pointing at each other, the ones that are covering the shelving area, I have a very good coverage. If I want to take a look at the signal strength, you will see that my signal strength is very high. And that means that I do have the coverage that I want. I do have a coverage that is greater than 73 dBm. So in that case, you know, I can claim success. And what I want to point something out is that there is always a question: what would happen if I do not take reflections into account? So here is, I'm going to enable a different prediction here that is going to show you what the coverage would look like if I decided that to take into account only a direct path and not take reflections. As you see, the coverage now all of a sudden has a lot of holes, and those holes are there because I only took direct path into account. So obviously, when you are calculating coverage, you have to have a direct path, and you have to have also reflected and diffracted paths to give a good presentation as to what is going on. I have also then ran a prediction for the coverage area in the offices, and they cannot be shown at the same time because those are two different technology. This is 8.11n, and the other ones are 8.11b and g. But as you see, those omnidirectional antennas, omnidirectional APs, will give good coverage there. So, having said that, you know, now we want to look at the co-channel interference to see what it looks like. And there we have about 65% has a co-channel interference of 1. Now this is actually a good news, because it means that we were able to isolate this signal very well. because the cultural interference of one only is not all that bad. So those directional antennas have been doing a good job for us because they were able to direct the signal where it should be with not much of a spillover. Now let's move on to the case where we have boxes in there. So let me see. Let me just move on to the warehouse with boxes. So this is how it looks like. Basically filled up those shelves with boxes. Shelves are about 3.5 meters tall, and boxes and about 3.2 meters. So you see there are some holes in between boxes. They're not full on stacked on one on top of another. So I basically showed you how it looks like with about 60% full. It could be 100% full, but I decided to show you just this example that they're partially full. And then you can view those antennas that I showed you earlier, how they look like here. So basically you see two antennas, one for 2.4, another one for 5 gigahertz. And, I tried to put them one on top of another, but I couldn't, so I put them as close to the wall as I possibly could. So the question is, how does that coverage look like once I have filled out those boxes? Remember, I only have one antenna pointing along this corridor. So there, signal strength prediction. Okay, so let's see, why am I not seeing prediction? Oh, this is N. Okay, so yeah, I know what this is. This is a wrong. Yes, this is the one. Okay, so this is signal strength prediction for B and G. And there you see now that I do have some holes in the coverage right here. My signal strength is lower than X73 dBm, which is not good. And obviously I cannot get by without putting additional APs. So what I'm thinking about doing is having to put another AP here, and here, and here, and also here, and possibly right around here as well, to improve the coverage. So once I do that, this is what I get. So now the coverage is better. I still see some areas where it's a borderline unacceptable, like this one right around here. It's neg 76, neg 77, also here and here. And you may think, okay, what should I do? Should I now put Ventev antennas there or what? Well, first, remember we said those shelves are tall. So what we need to do is we need to see what the coverage is not in just one one height of the shelf, but multiple heights of the shelf. So I ran prediction at 0.5 meter. And there it looks like it's about the same. Now, if you put them side to side, at one point, wait a minute, what is this? If you look them at the same area, you know, it is a little bit better, but mostly about the same. Okay, but so what would happen at 2.5 meters? Now at 2.5 meters, it's a different story. Everywhere the signal is above negative 73 dBm. So what is the conclusion that we can get out of all this? I have a very good coverage at 2.5 meters, but at 1.5 meter, there are areas where I would need to improve the coverage by a few dBs. Well, the solution would be to tilt those antennas downwards a little bit, maybe a degree or two. I do not have a map that would show you what the end result is if you down tilt by a few degrees. But given that these are narrow beam antennas, and given that they are mounted 2.5 meters above the floor, it stands to reason that you get the most gain at the height of that antenna. And I have just shown you what it looks at 2.5 meters, but it looks like at 2.5 meters, which is the same height as those directional antennas. If you want to have a good coverage that is below that height, you need to down tilt that antenna a little bit in order to move that peak coverage off of 2.5 meters. So that is how you would solve this problem. You don't need additional Vantev antennas to help you here. All you need to do is to down tilt antennas a little bit. So having said that, let's take a look at the co-channel interference. How does it look like when we have those boxes that are given here? Well, co-channel interference again is not bad. We have mostly 1 and 0, which again is because we have those directional antennas that are helping us out direct the signal in the direction that we want. So this, in a nutshell, is how you would approach a design of a warehouse. Try to use directional antennas and mount them on the opposite wall of the warehouse. Then try to find good directional antennas, external antennas with the narrow beams, and point them, directly into the corridor. Do the design with no shelves. Do the original design with no shelves. Get a good coverage there, and then model with shelves and fill in the holes. And that's what I did. I put those additional APs in the areas where I thought that the holes existed. And then in the end, if you still have some areas where your signal is a few dB lower than it should be, try lowering antennas if you mounted them high, maybe 2 or 3 meters above the ground, or experiment if you can with without tilting the antennas. I'm saying that mounting antennas 2.5 meters above the ground is a good idea because you will not have heavy machinery park itself in front of the antenna that maybe is 1.5 meters above the ground. You do want that antenna to be above the machinery that passes through, or the machinery that can be parked along the side of the wall. So that's why I would go with 2.5 meters or even 3, and then down tilt later on to improve the coverage at the lower points of the shelf. Remember, you do need to cover shelves maybe higher than what I have shown here. If your shelf is 15 meters tall, then I'm sorry, not 15 meters tall, 15 feet tall, then you need to go and have another a point or two to examine the coverage, maybe along 12 feet above the ground or 14 feet above the ground. And so keep in mind the height of those shelves when you want to decide, when you go to decide how high that antenna needs to be mounted on the floor. And with that, I'm going to turn over to Kelly, and we can take questions.
Sure. So one here is, what is the impact of metallic or reflective surfaces and structures on 900 versus 2.4 versus 5 and their associated advancements such as MIMO?
Okay, so I have shown you what the effect of reflective surfaces is. I ran a prediction at 2.4 that clearly have shown if you do not take reflection into account, you are going to have a very different propagation characteristics. Here is again with no reflection, and you see there are holes, and then this is with reflection. Okay, so reflection has to be taken into account when you are doing the prediction. You just should not rely on a single array propagation analysis. How do we fight that? Now, MIMO actually thrives on reflections. But here we have 8.11b and G, and that is not a MIMO technology. Okay, so there, we may have an issue with excessive reflection, and that's when you disable your short guard interval with the hope that this will help with your BER.
Okay, can you explain the power levels choice for 2.4 and 5 gigahertz?
So why are they different, right? They're different because it's the propagation characteristics that is different. It is a little over a double of power. I'm sorry, a little of double in frequency, and what it means is 6 dB in propagation. So in 6 dB in a path loss differential, just because of frequency. And so you would want to have your power for 5 gigahertz at least 6 dB higher, if not more. Now, why not more? Maybe it needs more because antenna characteristics are not the same at 2.4 and 5. I have shown you the radiation patterns at 2.4 and 5. They are similar, but they are not the same. And your gains may be a little bit different. That's why in this case, I have decided to go even higher with power. Another reason is that the penetration loss for materials may not be the same at 2.4 and 5. At 5, it may be higher. So that's why it is not 6, it is 10 dB in this example. And I did not show you the 5 gigahertz coverage plots in the interest of saving time.
Okay, thank you. This question is, what is the suggested antenna system for warehouses? What about 700 megahertz? Does it cover the warehouse with full shelves?
Well, 700 is not a Wi-Fi technology, and here was an example of using a Wi-Fi technology to design IoT at a warehouse. So what you're concerned is 2.4 and 5 gigahertz and not 700. 700 is a licensed band that is used for LTE currently and possibly for 5G in the future.
Okay. This question is, if the boxes are empty in the demo, how can extra attenuation be taken into account due to the merchandise located inside the boxes, or what's the best approach to handle that?
Well, I have filled out the boxes. They're wooden boxes, and inside I assumed that they're not empty. I assumed paper inside. I assumed that this is a warehouse full of books. So that's how I accounted for the merchandise. The merchandise in this example was books.
Okay. This question is, what is the main difference between CBRS and Wi-Fi?
CBRS is technology that really refers to a concept of managed spectrum. Now, having said that, from a pure protocol standpoint, CBRS is LTE. So it operates at the frequencies that were designed as LTE frequencies by 3GPP and is only open to LTE protocol to be run on that frequency. So when you talk about CBRS, you really are talking about LTE protocol running on a spectrum that is a managed spectrum, which is neither licensed nor a licensed, but something in between.
Okay. This question is, do you need to do a CW and model the Wi-Fi propagation?
Do I need to do CWN? Do I need to know CWN? I recommend that you take CWN. Are you talking about CWNA, I guess? Sorry?
Maybe survey? Just a CW.
Oh, CW survey. Okay.
Yeah.
You need to do a CW survey to do what exactly?
And do you need to do both the survey and model the Wi-Fi propagation?
Okay. Yeah. I would suggest that you do both. You do not need to go and do that in this example along every area in a warehouse, just in between a couple of shelves. But the survey being done at Wi-Fi frequencies, it's usually done by using a spectrum analyzer to account for noises that exist, and it is always a good idea. CW can be done, but CW at 2.4 gigahertz, I don't think you can really buy a transmitter at 2.4. It's unlicensed band, and then I'm kind of puzzled as to how you can do that survey with using CW at 2.4. I personally could not find any CW transmitter. You can do a survey using Wi-Fi signals. You can get your AP, that is a thin AP, that is used just for sending signals on 2.4, and put it in a location where you think your AP will be located, and do the survey that way.
Okay, and just time for one last question here. What about designing Wi-Fi for coolers and freezers in warehouse environments? What do you suggest there?
Yeah, those are metal boxes. You will have to put one in there now, because that's just coolers and freezers. They're cold. I honestly have never done that, So all I know from our propagation standpoint is that you are not going to get any signal in there unless you have an antenna. If you can put an antenna in there through some kind of a hole in a refrigerator, and seal that hole off and have an AP outside of the antenna, that would be awesome. Otherwise, I don't know how an AP can operate at 0 degrees Fahrenheit if in a freezer, or which is -18 centigrade.
Okay, thanks very much, and that brings us to our time limit. So at this point, we're going to conclude the webinar. I'd like to thank everybody for joining us, and thank you, Lodan, for putting on such a great presentation. Thanks, everyone.
Thank you. Bye-bye.